Hello, this is Dr. Michael Hassan, the engineering doctor, and this is lecture number 41. Synchronous counters design with JK flip-flops of Chapter 7, Counters and Registers of the course Digital Logic Design for Digital Systems or Digital Electronics. This is a disclaimer for you to read. I cite 3 references in digital logic design. However, there are many books available in this area. In Chapter 7 contents, we covered digital counters and ripple asynchronous counters, binary ripple down counters, binary ripple up-down counters, other ripple counters. We talked about design of synchronous counter using D flip-flop. Then we talked about the design of synchronous counter using T flip-flops. And in this lecture, we will talk about the design of synchronous counter using JK flip-flops. This is a very important lecture. I will show you actually a shortcut method to find the excitation of the flip-flop when we design with JK flip-flops. And the next slide is a reminder about the characteristic equation, which we covered before, and the requirements, the excitation requirements table of the JK flip-flop. So the characteristic equation Q plus is equal to JQ prime or K prime Q. This is a very important characteristic equation, and from this characteristic equation we can get with the shortcut methods to find all the excitations, namely the J's and the K's for all the flip-flops for any counter that we design. Okay, so the requirements, the excitation requirements when we change the state from 0 to 0, that means we are remaining at state 0, J has to be 0 and K don't care. 0 to 1, J must be 1, which is, this is the set mode, and K don't care. 1 to 0, this is the reset mode, K has to be 1 and J don't care. And 1 to 1, K must be 0 and J don't care, so J don't care and K 0. This table is very important in the design of any counter using JK flip-flop. Now, as an example, we will design a mode 8 synchronous counter using JK flip-flop, and the present state will be 0, 0, 0. Again, we need 3 flip-flops, Y3, because it's mode 8, 2 to the power 3 is 8. So from 0, 0 down to 1, 1, 1, we have 8 states. And those arranged, the present state arranged in sequence, binary sequence, from 0, 0, 0 to 1, 1, 1. Now the next state, if we have 0, 0, the next state will be 0, 0, 1. If we are in 0, 0, 1, the next state will be 0, 1, 0. So you can imagine we have the state graph in front of us, and we will go in circle until we reach 0, 0, 0, then we'll start again. Now, what we say, we have the transition from 0 to 0. A is 0, the next state is 0. How much JA needs to be and how much KA for this flip-flop? We are in the A flip-flop. So we look at A and A plus only. We look at this column, the A column and the A plus column. So 0 to 0, just we talked about it in this table. 0 to 0, we need 0, don't care. So 0 to 0, we need 0, don't care. So we have 0, don't care. Again, we have 0 to 0, 0, don't care. 0 to 0, 0, don't care. Then we have 0 to 1. What we need, JA must be 1. This is the set mode, and KA don't care. And so on and so forth. Let me finish this. Then we have 1 to 1, we have don't care 0. See, 1 to 1, 1 to 1, Q, if Q1 and Q plus is 1, we have don't care 0. So J, A will be 1 to 1 will be don't care 0, and KA will be 0. And then 1 to 1 again, don't care 0. 1 to 1 again, don't care 0. Then 1 to 0, we have don't care 1. 1 to 0, we have don't care and 1. Okay. 1 to 0, we have don't care 1. So JA will be don't care and KA will be 1. We do the same thing for B and B plus, and we to obtain JB and KB, and we do the same thing with C and C plus to obtain JC and KC, and we tabulate the table in front of us. Now, once we have JA, KA, JB, KB, JC, KC, we need to determine the Boolean or the switching function of each value so we can implement it in hardware. So we need to take this to K-map. How many K-maps do we need? 6 K-maps. And we draw K-maps for each variable, for each excitation input, for JA, for KA, for JB, KB, JC, KC. So we have those, the 6 K-map. 0, 0, 0, 1, don't care, 1, don't care. JA, see here? 0, 0, 0, 1, don't care, don't care, don't care, don't care. So we have the map for JA. Now JA will give me the best thing we can do. We can make a group of 2. The 0 will cancel with the 1 for the A, and I have BC. The same thing with JB. I will have a BC. Now JC will give me 1, and KC also will give me 1. Okay. KA will give me also BC, and KB will give me also C. Group of 4. See JB and KB, JA and KA, JB and KB. So we say the map will yield JA is equals to KA is equals to BC. JB is equals to KB is equals to C, and JC equals to KC is equals to 1. Now we can draw the counter circuit or network or logical network. So we have 3 flip-flop, flip-flop A, flip-flop B, flip-flop C, with the input JA and KA. Those are short-circuited. And we have BC, this is B, take it to the AND gate, and C, you take it to the AND gate. So BC, you AND it, we apply it to JA and KA. You have the clock pulse here. And JB equals to KB equals to C, JB equals to KB is equals to C, and JC equals to KC equals to 1. So we have the complete design is done. The only thing we would like to talk about the shortcut method. Rather than having really a 6K map, we can work with a 3K map. We can look at here. So rather than generating this, as you see, it took us a lot of time to generate JA, KA, JB, KB, JC, KC. Okay, we can stay actually with the next state. And we will have 3K map, 1 for A plus, 1 for B plus, and 1 for C plus. What should we do? We look at the characteristic equation. Q plus is equal to JQ prime or K prime Q. Or we say A plus is equal to JA, A prime, or KA prime A. So since actually the map, the K map, it is a plus map, but the A plus map could be divided to 2 maps. One is the A prime map to obtain J, and one is the A map to obtain K prime. Okay. To make it even easier, we go to the A prime map and we will simplify for the ones. So we group the ones to obtain JA. Since this is K prime, we will go to the A map and we group the zeros to get K straightforward, because when we have the complement of function, we group for the zeros. As you remember, we work with K maps. So we will group with the zeros to obtain K, directly K. Or we group for the ones to obtain K prime, then we complement the answer if we want to. What is better really to group the zeros, simplify with the zeros, and this will give me K straightforward. Okay, so let's look at this problem that we did. the mode 8 counter. I will have A plus K map, B plus K map, and C plus K map. And those K maps are shown here. 0, 0, 0, 1, 1, 1, 1, 0. See the A plus? 0, 0, 0, 1, 1, 1, 1, 0. Very good. So we fill up the midterms, and the same thing with B plus, and the same thing with C plus. Now we go to the A plus map, and we will divide the map. Where is the A equal to 0 map? The 8 equals to 0 of the A prime map is here, this side of those 1, 2, 3, 4. So we divide the map to A is 0 map and A is 1 map. We go to the A equals to 0 map and we group the ones. There's only one. When we group it here, what we will get? The answer BC. It is really BC A prime, of the A prime is the coefficient. It is BC A prime. A plus is equal to JA, right? JA A prime. So we ignore the A prime. We ignore the A prime. The same thing here. We go to the A equals to 1 map and we group for the zeros, and also we get BC, BCA, and A will be ignored. So KA will be BC, grouping for the zeros. So we say KJA is equals to KA is equals to BC. Super easy. It's very simple. The same thing, we go to the B plus map. Now we will divide the map to B equals to 0 map and B equals to 1 map. Where is the B equals to 1 map? B equals to 1 map is the last, is the 4 cells at the bottom, the 4 midterms at the bottom. And the B0 map is the 4 midterms at the top. So this is the division between the map. This is the division. See the pointer here? Okay, this is the division. So we go to the B prime map or B equal to 0 map and we simplify for the ones to obtain JB. So this is the JB map and we find a pair. The 0 will cancel the 1 horizontally and we will ignore the B because this is B is the coefficient. So the answer is C. So we say JB is equals to C. It is really CB prime, but B prime is the coefficient because we are in the B0 map. So we ignore it, so it will be C. And if we look at those at the B1 map, we will go for the zeros, and we get what? We get K. Directly, we get KB. So those zeros also will give me C, So we say JB equals to KB is equals to C. The same thing we do with the C plus map. With the C plus map, we have 1, 0, 1, 0, 1, 0, 1, 0 from the table. See, 1, 0, 1, 0, 1, 0, 1, 0. We go to the map, we fill up the map, we divide the map. Those cells in the middle is the C equals to 1 map, okay, because C is 1. And we will group the zeros to find K. So when we group to the zeros, everything will cancel horizontally, everything will cancel vertically. So KC will be equals to 1. And the upper 2 cells and the lower 2 cells at the bottom will represent the C equals to 0 map or portion of the map. So we go here, we group those ones with those 2 ones. It's a group of 4. And again, everything cancels horizontally, everything cancels vertically, and the JC will be equals to KC and equals to 1. So the answer is correct. It's super easy, very simple. Again, we don't take C prime and C because they are the coefficient of J, C, and KC, okay? Because we are partitioning the map to a smaller order. And by doing this, we don't have to generate JA, KA from the excitation requirements table, from this table. We don't have to. And this shortcut method works for the JK flip-flop only because of the beauty of the characteristic equation here. We can work with the A plus map, B plus map, and so on and so forth. Okay, so we get the same answer, and this would be the end of the design of synchronous counter using JK flip-flop. I would like to thank you so much for listening. Please subscribe. See you soon in the next lecture. Sincerely, Dr. Hassan.